Hello everyone, I'm excited to present our work ArchitectHead, Continuous Level of Detail Control for 3D Gaussian Head Avatars. In 3D meshes, level of detail control is a well-established technique to balance quality and efficiency. However, there are some challenges in 3D Gaussian splatting-based methods. Because unlike a 3D mesh, where vertices are connected and can be simplified using standard methods, 3D Gaussian splattings are unstructured, ellipsoid-like primitives. Therefore, even nearby Gaussians might have completely different attributes, such as scales, rotations, and colors. Therefore, we cannot simply merge nearby Gaussians to reduce the point count without causing massive visual artifacts. Our key idea is to achieve continuous level of detail control by treating Gaussian density like 2D image resolution. This is a proposed pipeline. In the beginning, we use the flame head model to get the 3D head mesh from the estimated head coefficients, including shape code, expression code, and poses. Then, we rasterize the head mesh surface to a UV position map with given UV map resolution. Each pixel on the map corresponds to a 3D Gaussian. We propose the learnable multi-level UV feature field along with a weighted resampler to sample the UV feature map with the same resolution as the UV position map. We train a mapping network to map the face and mission-related codes to the driving code and concatenate with the desired LOD value, and finally concatenate with our UV feature map pixel-wisely. We train a decoder network to decode the 3D Gaussian attributes ready for rendering. The proposed multi-UV feature field is a set of UV feature maps with different resolution from S1 to Sn. We can sample a new UV feature map from the UV feature field, where the expected resolution S is computed based on the level of detail L, where 0 indicates the highest level of detail and 1 indicates the lowest level of detail. The sampling is based on this equation, where the blending weight W is calculated based on how close the expected resolution is to the current feature map in the UV feature field. And I is the 2D bicubic interpolation function. Our training loss function has two sets of loss terms, the reconstruction terms and regularization terms, mainly following existing works. Because for lower level of detail, the size of 3D Gaussians are usually larger than in the higher ROD cases, the weight for the 3D Gaussian scale regularization term is partially calculated from the ROD value. The training has two stages. In the first stage, we render with the highest level of detail. And in the second training stage, we render with 5 selected level of details ranging from 0 and 1. Next, we show some results of self-reenactment experiments. Here are some cross-reenactment results. This is a demonstration of a continuous level of detail control. Thanks for your attention. Our project homepage has additional resources, including the demo videos and code.